Right. So here is our plan for today. We're going to start off by discussing the 1.7 homework, which will be hopefully a good review for part of the material you're going to have on your test Thursday. More on that in a second. But after that, we're going to go ahead and move on to the next lesson where we're going to analyze vertical asymptotes and holes. Going into tomorrow, we'll talk about the homework for 1.8. Hopefully, we should be able to finish up the current lesson. And then on Thursday, we have our exam. So it is going to cover lessons 1.4 to 1.7. How many people have started filling out your 3x5 note cards? Okay, so a couple. Okay, so if not, you still got a couple of days. I mean, I would definitely go back through each one of those lessons. Anything that you're having a hard time remembering, or maybe you're having some difficulty with, go ahead and put that on your card. Does anybody need one? Okay. If I can get this out. Anybody else? So we'll take the test on Thursday. Friday, I'll go ahead and pass them back. We'll talk about them. And then moving on into next week, we'll just hopefully get really close to finishing up Unit 1. Okay. So questions about what's happening? Okay. Did anybody need a copy of 1.7? That was signed. Okay. I do have a couple here. So there are 3 that I want to go ahead and start with. Anybody else? Okay. Because like I said, the test is coming up on Thursday. This one was trying to determine if a rational function had a horizontal or a slant asymptote. Now, while numbers 10, 11, and 12 do that, we also are going to write out the limit statements. So I thought that was a pretty good representation of the lesson. Okay, so let's take a look at number 10. All right. So in order to determine if it has a horizontal or a slant asymptote, we got to compare the what? Degrees, yeah. Okay, so let's look at 2x cubed minus 5x plus 6. Okay, Quinn, what's the degree of the numerator? It is 3. And we have 6x cubed plus 10x squared minus 4x minus 12. Okay, Bailey, what is the degree of the denominator? That is 3. So this right here is case number 1. This is if the numerator and denominator have the same degree, bless you. So it's going to be a horizontal asymptote. In fact, can anybody tell me what that is? It should be y equals what? Or not 0. That's if it's case number 2, if the numerator's degree is less than the degree of the denominator. I can't talk today. So can anybody tell me what it is? 3, we're getting closer. It is 1/3. Where did I get the 1/3 from? There we go. There we go. See, if the degrees are the same, then you take those leading coefficients, the coefficient that belongs to the terms that gave you the degrees, you go ahead and divide those. So 2, 6 is 1/3. So now I'm going to use this to write out my limit statements. So the limit as x approaches negative infinity, so that means the left end behavior of y equals, and the limit as x approaches positive infinity of y, that means the right side, equals. Well, because there's a horizontal asymptote, as we push out in both directions, it doesn't matter whether it's curving from above or below, the graph is going to get closer and closer to this horizontal asymptote, which has a value of 1/3. So that's the end behavior if there's a horizontal asymptote. Whereas we're going to see again later, if there's a slant asymptote, then it's either going to go to positive or negative infinity. Okay, questions about 10? Okay, well, let's try 11. All right. So let's see here. If I look at the degree of the numerator, that is going to be 2. Okay. If I look at the degree of the denominator, x times x squared, so that'll give me a degree of 2. So it's the same thing. We're going to divide the leading coefficients, but you got to be careful because this one's been factored. So let me go ahead and write this out. The limit as x approaches negative infinity of y, and the limit as x approaches positive infinity of y. Okay. It is an improper fraction. Can anybody tell me what these should equal? 8 over what? Yes, 8 over 3. That is exactly right. Okay, so let's talk about how we got that. Now, you don't have to completely multiply these out and expand, but you really just want to go ahead and focus on the first terms. Like this 4x right here, if I square it, that would be 16x squared. Let's multiply the first term of each of the groups down below. 3x times 2x would give me 6x squared. See, that's where I got degree of 2 and a degree of 2. But now when those cancel, my leading coefficients would be 16/6. That's where we got the 8/3 from. Now, if you want to multiply the whole thing out, I mean, you're more than welcome to. Okay. I just don't think it's necessary. All right. How are we doing? Does it start to come back to us? Okay. And here is our last one. The limit as x approaches negative infinity of y, and the limit as x approaches positive infinity of y. Okay, so I'm looking at this rational function here. Who can tell me what it should equal? It's not going to be an infinity, it's going to be a value. What's that? It is 0. Here we go. The numerator has a degree of 2, the denominator has a degree of 3. This is the second case where the numerator's degree is less than the denominator. If that's the case, it's still horizontal, but it's the x-axis. Y equals 0. Okay, good. Now, this is going to be a good lead-in to what we're going to be doing today as well. But before we go ahead and put this away, were there any other problems on 1.7 that we wanted to take a look at? Yeah, let's look at 16. Okay, so on the back, it's telling me verbally what they want, and then we write a limit statement given the graph. Okay, so this one here in number 16, it says the input values, so we're talking about the x's, okay, it says they're going to decrease without bound. So what this means in notation, this means that x is going to approach, well, how would I show that values are going to get smaller and smaller and smaller? We actually just saw it on a few of the previous problems. Negative infinity. Okay, so the input values decrease without bound, x approaches negative infinity. They're saying the exact same thing. So remember, if we approach negative infinity, we're talking about the left side of your graph. So for this one, the limit, as x approaches negative infinity for k of x. Okay. After this one here, what do we have as an asymptote? Is it horizontal or vertical? Oh, sorry. Is it horizontal or slant? It's slant. Because it's a slant, that means my end behavior is either going to be a positive or a negative infinity. If it's a horizontal asymptote, well, then your answer is going to be the value of that asymptote. Now, we're looking specifically on the left. So as x becomes increasingly small, the y values are going to get closer and closer to that asymptote, but you'll notice they are increasing. They're getting larger. So this is going to be a positive infinity. So for this one here, if the slant asymptote drops to the right, well, it's going to positive infinity on the left, and it's going to negative infinity on the right. Okay. But if you have a slant asymptote with a positive slope, well, then they're reversing that. Okay. So to the right, the y values are going to positive infinity. On the left, the y values are going to negative infinity. Is everybody okay with that? Okay. Does that help out? Now you asked about that one, huh? Okay. Anything else? Okay, fantastic. Let's go ahead and put that away. Unless, is anybody ready to turn that in? Okay, hang on to it. All right, let's put that to the side. Here we go. Now, lessons 1.9 and 1.10, they were merged into a single lesson because even on their own, that was way shorter than we needed. So this worked together perfectly. Okay, so we're talking about vertical asymptotes and holes here. So recall that a rational function is the quotient of two polynomials. We already know that. If I take a polynomial and divide it by another polynomial, we're going to have a rational function. Super easy. Here's the thing. every lesson on rational functions, we're learning more and more about these. So we're still going to take the numerator and the denominator. We're going to factor those completely, if not already done. We're going to set each part equal to 0, and these values are going to mean something to us. Any value of x coming out of the numerator, that's called a root. That's going to be an x-intercept. So if I were to look at the graph, that's where the graph will be touching the x-axis. Okay. Now, what we're going to focus on in this lesson is the denominator. Any values making the denominator 0, what we previously called undefined, those are either going to be vertical asymptotes or holes. These are the values that we have to throw out or exclude when we're talking about, say, the domain, which we're going to start doing next week. So how are we going to tell the difference between a vertical asymptote and a hole? Well, I'm glad you asked. Okay. A hole, or also known as a removable discontinuity, occurs when the factor in the denominator cancels out with factors in the numerator. Okay. So once you factor, if you have anything that can cancel involving x in the numerator and denominator, you got yourself a hole. Okay. Now, a vertical asymptote, or also called an infinite discontinuity, occurs when a factor in the denominator cannot cancel out with factors in the numerator. Okay. So whether you have anything that cancels or not, hole aside, anything left in the denominator that makes it 0, that is going to be a vertical asymptote. Okay, so let me give you some examples here. This first column, this is all about holes. Okay. All right, now, what does a hole look like? So you've probably seen it before. In fact, you might remember in algebra and rational functions, we talked about finding a hole. You remember that, right, Vera? You remember all that? All that good stuff? Yeah, okay. So here's an example of a hole. You're going to see a graph just like any other, but on some part of it, you're going to have an open circle. It's like that one particular coordinate, that ordered pair, was just plucked from the graph, just removed. That's what we're calling a hole. So take a look at this first one up here, f. It says x minus 1 times x plus 2 over x minus 1. Okay. Do you notice anything about that function? There you go. See, we got a common group in the numerator and the denominator. If you can cancel a common group, that's how you know there's a hole. Okay. Now, we're still going to take the group that we marked out, in this case x minus 1. I'm still going to go ahead and set it equal to 0, so I know that the hole occurs when x equals 1. Okay. That's how we know if we have a hole. Something's got to cancel. Okay. We'll take a look at the one right below it. X minus 1 cubed over 2 times x minus 1 squared. Okay, well, we got 2 x minus 1s below that cancel with 2 of the same groups above. Okay. Now, if you have group factors that cancel, but one of those canceled groups is still left in the numerator, that's a hole. That's still going to be a hole. Okay. So I would still set it equal to 0. I do the whole thing. Okay. Now, that's how we know if there's a hole. Well, take a look at the second column. Let's look at vertical asymptotes. X minus 3 times x plus 2 divided by x minus 1. Okay. What cancels here? Nothing cancels. So there's no hole. So what I'm going to do is I'm going to take a look at the denominator. Whatever's in the denominator, I'm going to set it equal to 0. So if x minus 1 equals 0, x equals 1, that's where my vertical asymptote is. Okay. Now, this is just some FYI, but I'll go ahead and throw it out there again anyway. Remember, in this case, what minus 3 would be 0? 3. And what plus 2 would be 0? Negative 2. You remember what I said a second ago? That's not the point of the lesson, but I want to throw this idea out there. Any values making the numerator 0, remember, those are your x-intercepts. So if I were to look at this graph, it's going to come in contact with the x-axis at 3 and negative 2. Okay? Even though we're talking about vertical asymptotes and holes, I just want to throw that out here. Now, here is where some people can get a little confused. Okay? Let me ask you a question. How do we know if there's a hole? If something cancels, okay? There is one exception, okay? There's one time you can cancel, and it won't be a hole, it's going to be a vertical asymptote. This is what's going on in G. X minus 1 times x plus 2 divided by x minus 1 squared, okay? I can cancel the x minus 1s, right? Here's where you got to be careful. If you have factors that cancel, but one of those canceled factors is still left in the denominator, It's not a hole, it's a vertical asymptote. See, over here on G, when these canceled, one of the canceled factors was left in the numerator. That makes it a hole. Okay. So it is possible to cancel and not have a hole, even though 99% of the time, that's what you're going to be looking for. Okay. Well, let's take a look at how we're going to be viewing these with limit statements. So I wanted to kind of pull everything together, especially what we just did on 1.7, and show you this. Okay. Because given a limit statement, depending on how it's written, you need to be able to tell, is this referring to a hole? Is this talking about a horizontal asymptote? Is it slant? Okay. So if your limit statements have x approaching negative or positive infinity, but the answer is a constant, some number, you're talking about a horizontal asymptote. Okay. If x is approaching positive or negative infinity, but your answer is positive or negative infinity, you're talking about a slant asymptote. Okay. Now, how are the limit statements going to look if we're talking about a hole and a vertical asymptote? Well, you'll notice it's not approaching positive or negative infinity. It's going to be approaching an exact number. But I'm kind of confused about this. You see on the left, it says the limit as x approaches 1, but then it has a negative. What's that telling me? Reed, what do you think? What does that x approaches 1 negative tell me? Don't know. William, think no? No, good guess though, but not it. Right? Not quite. Okay. So this is the direction you're going to approach it horizontally. So if they give you a number with just a negative as a power, that means we're approaching that from the left. Okay. So what about the other one? The limit as x approaches 1, and then it's got a plus. That's approaching it from the right. There you go. Okay. So if x is approaching a specific number and your answer is a number, you're talking about a hole. In fact, this information here would tell me immediately I know there's a hole at 1, 3. Now, what's it going to look like if it's a vertical asymptote? Well, you're still going to have x approaching a specific number from the left and the right, but if your answers are some type of infinity, then we're talking about a vertical asymptote. Okay, now here's why. For this first example up here, they said we have a vertical asymptote at x equals 1. So let's say I have this right here. So this is crossing at 1. That's a 1 right there. So it's horrible. Just kind of go with it. Okay. Now, when we go ahead and graph a rational function, whatever it looks like on the right side, the closer it gets to the vertical asymptote, this graph wants to make a choice. It's either going to decide to curve up to positive infinity along the asymptote, or it's going to decide to curve down to negative infinity along the asymptote. It's going to do the same thing on both sides. So on the left side, it's going to decide to curve up, or it's going to decide to curve down. That's what this information here is telling me. In fact, one of the last problems we look at today, I'm going to show you how to do that. Okay. So are there any questions how to tell your limit statements apart? So that seems like a whole lot of information. We're talking about holes. Hole. Come on. Okay. Okay. Let's go ahead and put this into practice. Let's get some examples. Okay. So for A, B, and C, determine the x values of any holes or vertical asymptotes. So all we want to do is figure out what this graph has. Okay. So we have x minus 2 times x plus 3 over x plus 3 times x minus 5. Okay. Will this have a hole? A lot of people are saying yes. Why? Okay. So we have a group that cancels. So there's going to be a hole. Okay. Now, where does the hole happen? I'm still going to take that group that we crossed out, and I'm going to set it equal to 0. So the hole would occur when x is negative 3. Okay. Is there anything else that cancels? No, so that means that anything left in the denominator that can still make it 0, that's going to become your what? That's going to be a vertical asymptote. Okay, so I'm going to still set this x minus 5 equal to 0. So we're going to have a vertical asymptote at x equals 5. There you go. And it's very possible you could have 2, 3, 4, or more vertical asymptotes. Okay, it is very possible that could happen. We probably won't look at anything bigger than like 2 or 3. Okay, but it's still very possible. Okay. Now there is one last thing I want to show you on this before we finish up with A. One thing you need to be able, because next week we're going to start sketching these rational functions, so I need to know the exact location of the hole if there is one. Okay. So I'm going to go ahead and tell you that the location of the hole here, we already know that x equals -3, but I'm going to go ahead and tell you that the y value is 5/8. Now I want you to tell me, where did we get that 5/8 from? It is not random. It is very specific to this problem. Okay, Vera? What's up? Okay. Okay, so I think I know where she's going with this. If these two cancel, would everybody agree that what we have left is x minus 2 divided by x minus 5? That's all that's left after it cancels. Okay. Well, we already know that the hole occurs when x equals -3. So whatever x is left that did not cancel out, replace every x with what you have here. So in this case, up top, x minus 2 becomes -3 minus 2 over x minus 5, -3 minus 5. So you get -5 over -8. That's where I got the 5/8 from. Is that what you're trying to say? Okay. So does that make sense? Yes. I'm sorry, what? Oh, because a negative divided by a negative, that gives me a positive. So we just simplified the fraction. Okay, that's all there is. Any x that's left, plug that value you have in for every one of those x's for the whole. Okay. All right, let's try another one of these. Okay, so part B. All right, so it's already factored. Do you notice anything I can cancel? All right, so I heard x minus 2. So x minus 2 will cancel with one of the x minus 2's up top. And I can also cancel what? I can cancel a pair of x plus 1's. Okay with that? Now, we've got two groups left. I'm going to go ahead and say x minus 2 is equal to 0, so x equals 2. The other group, x plus 1 is equal to 0, so x equals -1. Okay. What I want you to do is take a few seconds. What are these? Are they both holes? Are they both vertical asymptotes? Is one a hole? Is one a vertical asymptote? Okay. Think about what we've said so far. Let's see if you can figure it out. Now, we'll go ahead and identify these, and then we'll come back and talk about the why. What about x equals 2? Is that a hole or a vertical asymptote? Can only be one. Okay, that is a hole. Okay. Let's see here. Alexandra, what about x equals -1? Hole or vertical asymptote? It's a vertical asymptote. Okay. Now, I do have one question. I thought that we had a hole when you cancel groups. So why is it -1 a whole? Remember, this is the one exception. See, I was able to cancel out a pair of groups, these group factors, but one of the factors was still left in the denominator. If that happens, it's not a whole, it's a vertical asymptote. But for the other one, the x minus 2's, when those canceled, that left a group up top. If it's left up top, that's a whole. Okay. In fact, can anybody tell me what is the location of the whole? It should be 2 comma what? 2, 0, yes. Because once I cancel out these groups, would everybody agree that what I have left is x minus 2 over x plus 1? Okay. I take this value of x that I have, the 2, and I just substitute it in. So I get 0 over 3, so that's why I have 0. So the whole should occur at 2 comma 0. How are we doing? Anybody not sure how we're getting this information? Does anybody have any questions? Okay, let's try C. Now on C, we've got 1 over x cubed plus 4x. So this one is not factored, so that's what we're going to do first. So 1 over, how would I factor that? Okay, x is a GCF. So if I pull out the x, what's left? There we go. Okay. So let me ask you about this one. Is there a whole? Why not? Nothing cancels. Okay. So one less thing to worry about. Okay, so there's no whole. Okay. So that means that anything left in the denominator, I want to set those equal to 0 because those are going to become my what? The numerator, that becomes the intercepts, but the denominator, that become vertical asymptotes. So it's like the zero product property. This first one, x, so I'm going to have a vertical asymptote at x equals 0. Okay. Now let's set the other one equal to 0. So if x squared plus 4 is equal to 0, that means that x squared is equal to a -4. How do I get rid of the square? We're going to take square root. What's about to happen? There you go. We're about to take the square root of a negative, which means I'm going to get an imaginary value here. So we're only talking about real numbers that would make the denominator 0. Because this one imaginary, we're not getting anything out of it. There's no real value of x that'll make that 0. So we only have one vertical asymptote at 0. Question. Okay, we're almost done. We got one problem left. Okay, 2a. It says write a left and a right limit statement as x approaches 2 for each of the following functions. Okay, so I got x minus 1 times x plus 3 divided by x minus 2. Now, it wants me to focus specifically on 2, whether it's part of a whole or a vertical asymptote. Okay, so for this one, is there a whole? Okay, no whole. Nothing cancels. Okay, no whole. Okay. So that means I'm going to focus on the denominator. I'm going to go ahead and set it equal to 0. That means I've got a vertical asymptote at x equals 2. Is everybody okay with that? Now, we don't have a graph, but we need to figure out if we're looking at the vertical asymptote, what's the graph going to do as it approaches it from both sides? Remember, we said a few moments ago, it has to go up or it's going to curve down towards the asymptote. So let me write out my limit statements here. So the limit as x approaches, how would I show 2 from the left? There you go. I'm going to put a negative right with that 2. This is of f of x equals. So the limit as x approaches, how do I show from the right? Positive of f of x. Okay. Well, we've been working quite a bit recently with sign charts, so we're going to use that idea to help me figure out what's going on here. So let me go ahead and create a line graph. Okay. Now, we don't have to worry about all of these. We're only interested in the vertical asymptote, right? So let's say this represents the x-axis. Here is my vertical asymptote at x equals 2. Okay. So I'm trying to figure out, is the graph going to curve up towards that asymptote, or is it going to curve down towards that asymptote on both sides? So I need to know whether it's positive or negative. Okay. Well, here's the thing about this. Normally, we would choose any value on either side, and we go ahead and plug it in, right? Okay. Here's the thing about this. You want to be careful. The further away you get from the asymptote, the more likely it is that you could get a false positive, meaning it could give you the wrong sign. Okay, so we're going to go ahead and choose a number that's to the immediate right and left of my vertical asymptote. Okay, so I'll do something now. Hey, were you knocking for a long time? Oh, 20 seconds. That's not too bad. Okay, so the way I was taught was to use a tenth. Okay, I'm going to go ahead and teach you folks the same thing. Because what's the relationship between a graph and its asymptote? What are they going to want to do? Do they want to cross? They're going to want to get as close as possible, but never what? They will never touch. Okay, so let's say we're going to go with a tenth. So if I go 1/10 above 2, well, that's just 2.1. So what would be 1/10 below? 1 point what? 1.9. We're going to use these values just like we did with the sign chart. We're going to plug them in, and we're going to see what we get. Okay, so let's see here. First off, a 2.1 minus 1, well, that's a positive. Remember, I'm still not interested in the number. I just want to know if it's positive or negative. Okay. What about a 2.1 plus 3? That's what? Positive. And a 2.1 minus 2? That's a positive. So this is a positive interval. What this means is that when I look at the graph, on the right side, at some point, it's going to want to curve up towards positive infinity on the right side. So that means for this limit statement, I'm going to put positive infinity. Okay. Now I'm going to do the same thing on the other side. Okay, so 1.9. 1.9 minus 1, that's a positive. 1.9 plus 3, that's a positive. You see how I'm mimicking the rational function over here? Okay. What's a 1.9 minus 2, though? That's a negative. That means this is a negative interval. So whatever the branch looks like, as it gets closer to the asymptote, it wants to do what? It's going to want to curve down. So what should the other one equal? Negative infinity. Okay. In fact, I can even prove this to you. I've already got this function graphed in the calculator. So let me come on over here. Okay. This is the graph of x minus 1 times x plus 3 over x minus 2. It has a slant asymptote. But we're talking about the vertical. Let me show you the vertical right here. So here's x equals 2. And you'll notice it's curving up on the right. What's it doing on the left? It's curving down. See, that's what we're trying to figure out. Okay. How are we doing? Questions? Wow. Man, we're done. We got 15 minutes left. Keep going. Oh, look. I think that may have been Ayla. No? Came from that way? Over here? What? Okay. All right, we'll stop today. So we will wrap this up tomorrow. Now, one quick question. Poles and vertical asymptotes. Is this on the test? No. No. It only goes through 1.7. This is 1.9, 110. Okay. Now, you will have limit statements because that was in 1.5, 1.6, 1.7, but not dealing with holes or vertical asymptotes. Okay, let me go ahead and get this set back up for the next class. That is not what I wanted. Okay, so if you want to go ahead and get your cell phones, you are free to do so. Okay.